Greetings to all the viewers. Now we are going to conduct the session based on alpha terpeniol. Alpha terpeniol is the natural product. It is the part of terpenoid compounds. Alkaloids and terpenoids are naturally occurring compounds. This is the content retrieved from textbook of natural products nurturing livelihood. This textbook is meant for all the natural products only. Natural products are having various kind of applications in the day-to-day life of human beings. That is the reason why we are going to focus, we are going to stress upon these natural products only, right? So whenever we are going to consider about the natural products, so many examples comes into the picture. You may go with the vitamins, proteins, hormones, enzymes, carbohydrates, lipids, fats, so many kind of materials are taken into the example of natural products only. In that, we are going to discuss about these natural products called terpenoids. Alkaloid content is already completed. Whatever series of sessions we completed, all are available at the channel called the World of Competitive Chemistry. Now we are going to discuss about alpha terpeniol. In that part, its extraction process got completed. Structural elucidation is also we finished just now, and we entered into next series called the biosynthesis of alpha terpeniol. The biosynthesis of alpha terpeniol proceed for the geranyl pyrophosphate. Geranyl pyrophosphate taken as the precursor, starting material, which releases pyrophosphate to give the terpenyl cation. Terpenyl cation is the kind of intermediate. This carbocation is the precursor for many terpenes and terpenoids. Its hydrolysis gives the terpeniol, right? So starting material will be geranyl pyrophosphate. If you observe that when geranyl pyrophosphate will be taken, so pyrophosphate moiety if fragmented, so this fragment is removed, what happens? This carbon is susceptible to bind up with this carbon. Whenever here the linkage is taking place, so these electrons are moving upwards. So here the carbon experiencing positive charge. So this carbocation will be originated over there. Now we are going to form this carbon able to bind up with this carbon also. There is a provision, there is a possibility. That is the reason why so many kind of final products you could achieve here. Simply the carbocation is located with the hydroxyl functionality. If it is treated with hydroxylation, means hydroxy functionality is added over there, so that here you can simply achieve alpha terpeniol. Or else this is the intermediate where this ring elongation taking place in the intermediate, right, which is not isolated. That is the hypothetical intermediate able to remove the proton. Proton, if removed, there is the formation of alpha pinene. This is the molecule said to be alpha pinene. Same geranyl pyrophosphate that able to generate either of the pathway you can proceed with the in both the steps, in both the process, in order to achieve alpha terpeniol and also alpha pinene. The intermediate compound will be, it is resembling with a certain extent alpha cymene, right? Alpha cymene molecule only, but instead of benzene ring, we are having the kind of cyclohexene analog. So this is the one which with the treatment of hydroxyl functionality, simply you can achieve alpha terpeniol, or else ring expanded intermediate able to proceed with the alpha pinene final product. So this is the biosynthetic pathway for the synthesis of alpha terpeniol. Synthesis is started with alpha pinene also. Hydration of alpha pinene acidic medium taking place. Formation of terpenyl hydrate is possible. Dehydration alpha terpeniol final product could be achieved. Alpha pinene is the starting material. Sulfuric acid water if treated, terpene hydrate will be added. So terpene hydrate intermediate is boiled, so that alpha terpeniol will be the final product. This is the way synthesis of alpha terpeniol will be successfully achieved. Starting with alpha pinene. Alpha pinene is the starting material you can clearly observe. It is the bicyclic ring system with the aldehyde functionality. Cyclohexene is the common feature. Hydration, addition of water, so that here the ring opening reaction, and whichever this cyclic ring is there, that opened up, and alpha terpeniol simply originated. So this is the way synthesis of alpha terpeniol, starting with alpha pinene. Let me go with limonene. Limonene is also neither precursors to generate this alpha terpeniol. Limonene can be treated acid catalyzed conditions like hydration. Hydration means addition of water taking place. Finally, you could achieve alpha terpineol as the final product. So, limonene is meant for cyclohexene ring with a methyl and isopropenyl group over there. So, that simply added with water. Whenever water added, here the hydroxyl group will be added, and here the hydrogen will be added, remaining top side skeleton unaffected. So only the bottom exocyclic double bond more reactive over the endocyclic double bond. Everybody aware. The reason behind that will be steric hindrance. Open molecule freely reacted, but the cyclic molecule rigid to react right within the molecule. That steric strain is operated. That's the reason why whenever water is added selectively, exocyclic double bond go for the hydration rather than endocyclic double bond. Simply, you can achieve alpha terpineol as the final product. This is started with limonene. Limonene is having two double bonded positions, but outside double bond will be hydrated. Let me go for the industrial synthesis of alpha terpineol, how we can synthesize in the bulk scale. Now, laboratory synthesis taken in the minute quantity, some milliliters of the compound reagents added and tiny molecule formation. That is a confirmation whether the viable method we are applying or not. That only the procedure you can apply in the laboratory pathway. But the purity of the compound is also taken into the consideration. How we extend the product formation starting from the starting materials, that also consideration. But industrial scale, we need to take the starting material in the bulk quantity, and the final product is also usable scale. That's the reason why industrial method of synthesis is very important. After succeeding in the laboratory, you can expand this, explore the method for industrial preparation also, based on the quality and the purity, right? Sulfuric acid hydration of turpentine oil fractions able to generate this alpha terpineol in the high grade quality in the industrial scale, right? Let me introduce that entire mechanism. I'm taking terpene. Terpene means here the hydroxyl, here the hydroxyl, no double bonds, nothing is there. Here is the cyclohexane ring system, hydroxyl over this bridgehead carbon, and here also bridgehead carbon is located with hydroxyl. Let me heat this. Whenever heating is required, hydroxyl removed. Here is the double bond formation. And this OH remains as such, which is called alpha terpineol. Alpha terpineol not generated alone. In addition, you may achieve another byproducts also, because whenever this is heated, another provision, the hydroxyl remains intact, that unaffected, and hydroxyl at the outside carbon atom will be dehydrated, giving rise to exocyclic double bond. In another provision, there is a dehydration in between these two carbons also, right? So that beta terpineol, gamma terpineol, also the fractions which you could achieve, mixture of terpeneols generated by means of heating and the simply dehydration process of terpene, right? So this is the way industrial scale synthesis is possible. Whenever this kind of provision for the synthesis, large scale synthesis is possible, simply you can go for the column chromatography, or else separating funnel separating methods will be there. Fractional distillation you can apply in order to separate the mixture. So this is the way kind of industrial scale alpha terpineol is possible. Even cetrol is the starting material in order to synthesize this alpha terpineol as the final product. Let me discuss in detail about how cetrol will be transformed into alpha terpineol within the laboratory. Cetrol, if taken, reduction is applied. Reduction is whenever reducing agent is added in comparison to the double bond, aldehyde is more susceptible for the reduction, being it is highly reactive over the double bonded functionality. So that the aldehyde simply turned into hydroxyl functional group, which is called a geraniol. Geraniol is the kind of essential oil once again extracted from the rose petals. Right now, you may go for the ring closure reaction. Further dilute sulfuric acid is applied upon this geraniol molecule. Slowly, the reaction closing the ring system with the dehydration process. Simply, you can achieve this alpha terpineol as the final product. The same citrol, another isomer you can go for. This is the kind of trans isomer. And here is the kind of narrow cis isomer will be there. Reduction taking place, again hydroxyl ring closure under acidified conditions, being it is very fast reaction. Within short time, alpha terpineol could be achieved. Why the rate of reaction is matter? with respect to geometry, that depends upon its orientation. If the orientation is suitable, the molecule immediately go for the dehydration and cyclization. Subsequently, alpha terpineol product formation is instant. Whereas, if that is not in the synchronized form, if the functional group is away from that kind of enclosure portion, so that it may take time for the dehydration process during this reaction, completion of the reaction. This is the way geometry matter for the rate of the reaction. Geometry, rate of the reaction are directly related. Now, after synthesizing the compound either by the biosynthetic pathway or else you may apply the laboratory pathway as well. Either of the method, if you are working upon that compound synthesized finally, you need to go for its confirmation, right? You need to identify whether the compound synthesized is correct one or not. For that purpose, let me apply the spectral analysis. IR spectroscopy able to distinguish functional groups. Obviously, hydroxyl group will be identified by means of its a peak, distinctive peak at 3300 to 3500 centimeter inverse. This is IR spectroscopy peak at 33 to 3500 centimeter inverse. Hydroxyl group got confirmed. Carbon-carbon double bond is also there in the compound. Cyclohexene, that is elevated with the peak at 1640 centimeter inverse. Obviously, OH group, if present, CO stretching is also there. That is 1050 to 1150 centimeter inverse. This is another peak you can locate. IR spectrum give the valid information regarding the presence of hydroxyl, presence of double bond, presence of CO stretching. So these peaks indicates there is a kind of hydroxyl functionality with olefinic double bond within the compound. This is the IR spectrum for the molecule called alpha terpineol. You can look at 3300 peak corresponds to hydroxyl and 1100 peak corresponds to CO stretching. And one more peak will be there, 1640. 1640 peak you can notice over there that corresponds to the olefinic double bond. These many peaks will be there. Proton NMR is also very informative. Methyl protons. So in that cyclohexene, upside you can notice methyl, bottom side you can notice isopropyl. Methyl will give the peak at 0.8 to 1.2 ppm. Then methine able to OH containing carbon able to give 3 to 4 ppm. So this is the hydrogen corresponds to 3 to 4 ppm parts per million. Olefinic proton able to give, olefinic cyclohexene proton will be there, right? That able to give the distinctive peak at 5 to 6 ppm. OH group will give the broad peak and exchangeable. Deuterium exchange is possible. Deuterium exchange is possible that indicate either presence of OH or NH2. So here being a molecular formula is related with oxygen so that it indicates the presence, confirmation of hydroxyl functionality within the molecule by this proton NMR. Again, say that in NMR gives the nature or environment of the carbon atom, 70 ppm peak, alcoholic carbon will be there, and olefinic carbons indicated at 120, 140 ppm, aliphatic carbons 20 to 50 ppm, methyl protons, methyl carbon is there, right? That will give at 20 ppm around. So this is the way nature of C13 carbons will be indicated. This is the proton NMR estimation peak for alpha terpineol. You can locate this 1.82. 1.82 is this one larger one. So this is a methyl protons, 3 protons. And here the olefinic hydrogen is indicated at 5.3. So here is the 5.3 peaks. You can clearly notice a very tiny peak. And OH hydrogen peak at 3.6. 3.6, let me locate 3.6. Here is the small peak you can observe, right? Here 1.7, that bridgehead carbon atom hydrogen is having 1.7, 1.7 located within the complex peaks. 1.24, 1.24, these two exactly identical propenyl, isopropenyl hydrogens. So that 1.24, this is corresponding to 1.24 peak. This is the way 1.82 will be there, 1.24. 1.24 is the larger one, sorry. 1.284 will be at this position. And this is 1.74 peak, 1.74, 1.49. All these comes under in these complex peaks only. So that this is the way the entire conformation of proton NMR spectroscopy indicated for this alpha terpineol. Then C13 NMR. If you go for the C13 NMR spectra, C13 NMR, the compound nature of the carbon are understood. So just we already gone through that one, and the entire data is also provided which carbon corresponds to what kind of peak. Later on, mass spectroscopy meant for the molecular weight determination, molecular ion peak M by Z value, mass by charge ratio values indicated 154, so that molecular weight of this one will be 154. Fragmentation, if you are losing water, so that your entire molecular weight discarded with 18, so that able to give the another fragment. Typical terpene fragmentation pattern you can notice within the molecule, M by Z values are given over there. So initially M by Z 154 indicated 154. Can you notice 154 anywhere? Can you locate 154 peak anywhere? This is the one 154. This is the molecular ion peak here clearly observed. So this is about this alpha terpeniol mass spectroscopy indicated for M by Z versus abundance of the peak. By the spectral analysis got furnished. Let me go for the completion of the session. Alpha terpeniol content will be concluded by the application review. Here, obviously, it is essential oil, right? So the fragrance industry is the most common applicability you can notice. Lilac-like odor it able to exhibit. That's the reason why in the perfume, soaps, and detergent you can apply this alpha terpeniol. Pharmaceutical as an antiseptic, antimicrobial, this alpha terpeniol is applied. Topical formulation, in topical formulations also you can blend up this alpha terpeniol. Industrial use like paints and inks are incorporated with this alpha terpeniol. And in terpene synthesis, you can add this alpha terpeniol. Even in the food industry, like flavoring agent, being it is the essential oil, fragrance, it able to exhibit the fragrance, right? That's the reason why mixed up with the food ingredients, so the flavoring agent it will be. So this is the way applications are indicated for alpha terpeniol. It is a monocyclic monoterpene in the summary, derived mainly from alpha pinene and limonene, either of the compound taken as a starting precursor in order to synthesize the compound. Structure confirmed by oxidation process, dehydration, and the spectral analysis as well. Chemical analysis and spectral analysis together worked in order to confirm the structure. It widely applied in the fragrance, pharmaceuticals, even in the industrial purpose. So this is the way we are able to conclude the session. Hopefully this is informative for your preparation, and it will give the much information regarding the alpha terpeniol, being it is the natural product most important in the examination point of view, even in the research point of view to explore. Thank you very much for your patient listening. In the next session, you are going to observe, explore about camphor. Thanks a lot.